Chat. Wait, करना है ma'am. Okay. Now next we are going to have tutorial 2. The session chair of tutorial 2 is Professor Shyan Chatterjee, Javadpur University, Kolkata. Professor Shyan Chatterjee is a senior member of IEEE, was born in Kolkata, India in 1980. He received the Bachelor's of Engineering in EC department from Vidyasagar University, India in 2003 and the Master's of Engineering degree in ETCE and the PhD degree in Engineering from Jadavpur University, Kolkata in 2005 and 2015 respectively. He has worked as a scientist at Sameer, Kolkata from 2005 to 2009. He is currently working as a professor with the ETCE department, Jadavpur University. He has worked as a secretary and a treasurer of IEEE Kolkata section from 2015 to 2017. His research interests include microwave and millimeter wave antennas, SIW technology, design of microwave passive devices, and design of waveguide-based slotted array antenna and VLSI design. Now I would like to invite Professor Shyan Chatterjee on the dais. Sir, please.
Okay, so good afternoon to all. It's been a pleasure to host the second session of the tutorial, and I would like to introduce the speaker of the second session, Professor Dr. Sujoy Dev from IIIT Delhi. Professor Dev is a professor in electronics and communication engineering at IIIT Delhi. He is also serving as the Associate Dean of the Student Affairs. He receives PhD from School of Electrical Engineering and Computer Science, Washington State University on May 2012. Before his current position, he worked as an intern at Intel Lab, Hillsboro, Orlando. His major awards and achievement includes DST Inspire Faculty Awards in 2012, Outstanding PhD Student Award in Computer Engineering WSU 2011, winner of Indo-US Grand Challenge Initiatives from Affordable Blood Pressure Measurement Technologies in 2014, won Best Poster Award at ASP/DAC 2021, won Best Paper Award at INIS 2017. He is currently serving as IEEE CAS CSS Delhi Section Vice Chairman, Associate Editor of IET Computer and Digital Technique. He is a senior member of IEEE. So without any further delay, I think it's better to listen from him. So I'm welcoming Professor Dev. The dais is yours.
Thanks, Professor Shayan, and all the organizers for having me. It's really an honor to be here and discuss about some of the things which we are doing. So the title of my tutorial is Efficient Compute Platforms for Enabling the AI Revolution. And I am associated with a lab called Advanced Multi-Core Systems Lab, AMS Lab at IIIT Delhi. I'll briefly introduce about the lab going forward. Now, coming back to the topic, there are quite a few interesting terms in this title. So efficient compute platform. So first of all, I'll very quickly go through some of the relevant things which we need to understand to figure out why suddenly AI revolution, or everybody is talking about AI, irrespective of whichever field you talk about. Everybody is trying to solve something or other using AI or ML. Now, AI and ML is not something new. We all know the concept of artificial intelligence started way back in 1943 when evolution of artificial neural networks were thought about. Turing machine is a great example where Turing posed this question: by asking a question, we can distinguish whether it's a machine or a human. Followed by that, there are several other events which confirms that AI, the concept of AI, artificial intelligence, machines thinking something, is not new. People have been trying to do that. There are AI winter periods also in between. Many things were not moving forward because possibly the uh, platforms which are needed to collect that kind of data to make AI feasible were not there. The communication network which you need, or infrastructure which you need to make sense of all this data, or the compute platforms were not there. That's why there were several ups and downs in this journey of AI. But now many things are working for it. For example, we can store a lot of data. Memory has become really cheap. Communication has become really fast. And the other thing, which is the key, the compute platforms are becoming very, 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 very fast, low cost. Whatever kind of big data analysis you want to do, you can think of doing it on Amazon cloud services, or you can think of buying some GPUs to train your algorithm, or with lot of data, and then trying to infer from those learnings. So those things. So whenever we think about compute platforms for AI, we think of either GPUs, TensorFlow processors, or cloud services primarily. But all these platforms, or at least primarily GPU, was not designed keeping in mind to solve these kind of problems. So if we go back and see like how compute platforms are evolving and how the applications are driving that evolution, is something fascinating. And if we look from the fundamental point of view, possibly we can come up with more interesting, more reliable, more efficient solutions. So that's what I will try to basically touch upon in this talk. And I know it's after lunch session, so I'll try to keep this as interesting as possible and keep it as interactive as possible as well. I'll be very happy if you stop me and ask to elaborate something. And if I rush through, please feel free to ask for clarifications. Now we have seen how a history of AI looked like. And if you look at the history of compute devices, the kind of evolution or the kind of exponential growth we are seeing in number of devices we carry, the connected devices, at least all of us are carrying more than two or at least two connected devices these days. And going forward, this number might even increase because all of us will be having smartwatch or some maybe wearable health monitoring device, which will be constantly pumping data to some cloud service or something like that. So we see there is a very good correlation between how compute platforms are evolving from the mainframes of 1960s to, let's say, personal computers in 80s to our handheld devices in early 2000. And now we are in the era of many devices per user. So things are basically looking very nice. But uh, if we look at the other challenges, we keep hearing about death of Moore's law. All of us are aware that devices are not scaling at the rate which it used to, and because of that, we can't have the automatic high performance computers available to us. So we have to do something different. We can't make transistors whose channel lengths are possibly beyond, let's say, 1 nanometer or smaller than 1 nanometer. So what is the way forward? Now, what are the other challenges? So from the very early days of evolution of computer, the computers are thought as a stored program device. So basically you have program, you have your instruction, your data stored in memory. There is a processor. Whatever you need to do, you have to fetch the data, fetch the instruction from memory, execute it here, store the result back to memory. Now the problem is we can make our processor faster and faster by building faster transistors. The logic is really doing things very fast. But this communication of data, and with the basically the popularity of AI and ML algorithms, the amount of data has become really, really large. Now, how do we move this huge amount of data from memory to the compute element, the processor, and then store the result back in? So that has become the biggest bottleneck. So moving data is the most expensive and most uh, uh, basically the biggest bottleneck in getting higher and higher performance. So I'll primarily focus on my talk on how this interconnection network, which enables this communication of data, uh, more smarter, more optimized, uh, so that we can achieve better performance. Now, uh, we all know this answer, why we need more computing, because 10 years back, if we think of, maybe we never thought of we will stream the World Cup football final on our smartphones, right? 10 years back, it was not thought of. But now we can do that. I'm sure all of you have watched World Cup final yesterday. And it was happening real time. So if you look at some of these platforms, they are handling millions of subscribers at a time without any glitch. So all this is happening because there is a huge data center handling all this traffic. So, and I'm sure 5 years down the line, 10 years down the line, the needs will be different. We can't even possibly imagine what all we can do 10 years down the line. So that's why we need compute power. So we can't say that, okay, whatever we have today, that's enough. We don't need any more compute power, so we can just relax and be happy with it. That is not going to happen. So we need more and more compute power. Some people will think of very interesting ideas, possibly the metaverse and so on, which will require maybe 1,000 times more compute power, which we have today. And apart from that, to many of the challenges, both scientific as well as exploratory challenges, health related challenges, they need more and more compute power so that we can do things much better. Even simple things like natural language processing, to do it very accurately, we need more compute power. And many of the scientific communities are banking on the fact that the trend of getting higher and higher compute power looked like this in the past, and this trend will continue, and that's why 5 years down the line I'll be able to maybe have a better diagnostic on my handheld devices. So that kind of communities are relying on that fact that we'll have that compute power. Now, so to achieve that, what all we need to do? For example, the idea of exascale computing, that is 10 to the power 18 floating point operations per second, was not conceived, let's say, was conceived at least 10 years back. And today we have the fastest supercomputer. If you search top 500, you will find that the top 2 fastest supercomputers are actually capable of supporting exascale performance. And there was huge race between US, China to achieve that. So US has now one supercomputer which supports exascale performance. Similarly, Japan, Fugaku, that supercomputer is named Fugaku, it can support exascale performance. So it has huge implications, strategic implications, and so on. So we need compute power. There is no denying about it. More and more compute power. And we are already in exascale age. And the way this percolates lower down the order is that when we have a supercomputer with exascale performance, very soon we'll have single chip solution which will be able to sustain petaflop. So right now, the single chip, that the fastest single chip can sustain teraflop, but soon we can assume that some technological breakthrough will allow us to achieve petaflop functionality going forward. Now, another thing which I'm sure many of you observed and are aware of is that nobody is talking about single core processor. Even your mobile phones have multiple cores. And the reason behind it was the famous power wall. So before this multi-core era came in, most of this generational improvement in performance was we were achieving by clocking our processors faster and faster. For example, if many of you will remember Pentium series processor, it started with Celeron, which worked in megahertz, then Pentium 1 came, 2, 3, 4. Pentium 4 was running at 4 gigahertz clock. And then Intel at some point was advertising Pentium 6, which will run at 6 gigahertz and so on. But it never came because the clock frequency is directly proportional to the amount of dynamic power the chip consumes. And when you run faster and faster this processor and you have billions of transistors which are switching in a very tiny 400 millimeter square area, the amount of heat it generates is basically is not manageable. You can't use a cost-effective cooling strategy to cool it down. And Intel has very famous slides which was showing that if this trend continues, then soon the chip power density will be equivalent to sun's surface power density and so on. So definitely this was not the way to go forward to achieve higher and higher performance. So what was the way out? So again, researchers hit that power wall. So they thought, okay, I can't run one processor at a very high speed. How about I put two processors? Because I have billions of transistors. And in 2 more years, if I have 1 billion today, I will have 2 billion transistors in 2 years. So I have a huge amount of transistors. So I can make multiple cores. And instead of running each of them at a very high speed, I'll run them at a relatively low speed. But with the assumption that I can distribute the work I need to do among these cores in a proper manner. And I can achieve performance. So that's the whole idea of multi-core, and that's why we see that none of our laptops are single core anymore. Most of our smartphones are not single core, and this trend will continue even further. So there are basically Intel came up with their 80 core first I think teraflop sustainable teraflop performance multi-core system in way back in 2012. And then now all their cloud computers, which they have more than 50 cores and so on. But the trend was supposed to be much more faster. So basically, Professor Anant Agarwal, who is a professor at MIT as well as founder of Tylera, which is bought by EasyChip now. Tylera is a company which builds basically processors with hundreds of cores. He predicted or kind of given a corollary to Moore's law, saying that number of cores will double every 18 months. So Moore's law can be interpreted as number of transistors will double every 18 months, but he said that, okay, number of cores will double at every 18 months. But this did not happen. This did not happen primarily because there are other challenges. You can't really distribute your work at that scale. Most of our thinking is sequential. So we think that, okay, I'll do this steps. Now, if you say that, oh, I have 16 different workers to do it, how do we distribute that task among those 16 workers so that they are not dependent on each other or one is not waiting for the outcome of the other? Programming becomes difficult. Parallel programming has not picked up as it should have, and so on. Many of our very fundamental things. For example, let's say, how do you maintain coherence between the data which multiple, let's say, users are using? So if you look at that, you will see that there are, in computer architecture, there are two very popular protocols, coherence establishing protocol called Snoopy and directed. So and both these protocols, at least Snoopy protocol, actually, as the name suggests, it snoops, and it basically tells others that, okay, let's say I'm going to use this part of the data, so I tell others that if you have a copy of that data, so please invalidate, so that the update I'm providing, that you can use. So in Snoopy, the basic assumption is that you can tell everybody very easily. You can broadcast messages, this kind of things. But that comes with the fundamental assumptions that all your processors or all your nodes are connected to a single bus kind of structure where you can broadcast things. So I'll elaborate it little later. But that is not possible when you are talking about, let's say, 64 core, 128 core systems, because you can't connect them on a bus, and you can't instantly send this information to all your other competing processors. So because of these fundamental challenges, moving from single core to multi-core was not that easy, and that's why the kind of uh, progress we were expecting, that has significantly gone down. For example, when we were looking at the growth of processing power till 2000, it was almost 53% every year, whereas from 2000 onwards the growth is around 20%. So now even maintaining that 20% is becoming difficult, but our needs have not changed, so we are craving for more and more computing power. And for example, autonomous vehicle is a very interesting example about how more compute power enables a car to move on its own. But if you look at the current solution, whether it's Tesla, whether it's the Google car and so on, they need huge compute power, and it's possibly not affordable in most cases, and in very complex situations they will not be able to also function. So this is just a glimpse of how basically this evolution has already happened, and it's ubiquitous. The processor which could sustain 1 teraflop or the supercomputer will take 72 cabinets in the year 97, and now in 2000, basically in 2011 itself, we had a single chip processor which could sustain that kind of performance. So the impact internet, smartphone have on our life, it's expected that AI ML will have much bigger impact on our life if we have the right compute platforms provided to this AI revolution. So, and it's possible. There are many good signs that things are moving in the right direction. So one thing I'll not talk about in this talk, but which is also becoming very interesting is, instead, as I mentioned, like your data needs to be moved to processor. So there are many people who are thinking, why I need to do this movement? Can I not do some processing in the memory itself? So in near memory processing, in memory processing, these are becoming very interesting, but there are of course challenges. So possibly going forward, there will be a hybrid solution which will do something in memory, something for the processor will do, and so on. Now, before we move and look at some of the solution which we have worked on, I would like to go back to basically the fundamental of how a computing system works. So if you look at so as user, we are primarily concerned about application. For example, I want to do some let's say identification of cat or dog. So I have that application. So if I show a picture of cat, the algorithm should tell me that it's a picture of cat. And if I show it a dog, it should be able to identify it's a dog. Now, how it is getting done? If you look, basically look finally how it is done, it's some physics. Some electrons are moving, basically some transistors are getting switched on, and finally those transistors are telling me that it's a picture of dog or cat. Now if if I ask an engineer who is, let's say, fresh computer science graduate, and if I want to if I ask him to write this algorithm to distinguish a cat and dog, he will very easily write it. But if I ask him that how it is getting basically implemented on the hardware, I think it will be very difficult to connect the dots, right? Because I can see that, okay, this presentation is being live streamed, but ultimately some transistor or some electrons are moving, and that's how the whole thing is getting projected, and this basically everything is happening. But connecting this from application to this physics is a huge gap, right? So to bridge this gap, we as engineers, basically we are very smart. We say that, okay, whatever we don't understand, we abstract it out. We say that, okay, I understand this much, I understand the application, I'll tell you that, okay, these things I need. Now somebody who knows how this application can be translated to an algorithm, he will take these inputs and write an algorithm. Now he only knows that, okay, this is the input to this algorithm, and then algorithm output should give me this thing. And then somebody will write the program. It will be written in a proper programming language so that a compiler can compile it and translate it to a machine language. And then comes the hardware. So now, person who is writing the basically, or writing the compiler or giving the compiled output, for him or her, it's important to know that, okay, what kind of input the lower level should take, basically the hardware should take. That's where the instruction set architecture comes in. So instruction set architecture tells that, okay, basically to the programmer, this is the abstract out hardware. So I have this many resistors, I have this many, my bus width is this, I can do this kind of functionalities. It's an accumulator based system or it's a resistor based system. All these details are mentioned in the instruction set architecture. Now let's say I'm an microarchitecture designer, so I'll say that, okay, you need a x86 microarchitecture, so I'll design a hardware which can take any x86 instruction and implement it on hardware. Followed by that, there is register level basically implementation, followed by the gates, followed by the circuits, devices, and finally some basically how these transistors are working, basically the electrons are moving. So we have abstracted out all these different layers, and for a good reason. Most of us are expert in either one or two of these layers. And traditionally, we call this the middle three layers: instruction set architecture, microarchitecture, and register transfer level, broadly as computer architecture. But the more extended definition of computer architecture, or as a system designer, what should I know? If you ask, most of the designers will tell you that you should look into algorithm also, because you can optimize your algorithm depending on the hardware you have. If you are optimizing something at the algorithmic level and your hardware is doing something very different, then all your optimization at the algorithm level will not have any impact. Now, why it is important? It is understanding these abstraction layers are important because the application actually gives us the needs. They suggest how to improve the architecture. Basically, for example, let's say this AI or ML. So big data applications are coming. Now that's a need. You have to come up with some hardware platform which can take care of it. And readily available solutions were GPUs. So everybody jumped onto it, started using graphical processor unit for doing this big data crunching. And these applications also drive revenue. For example, autonomous vehicle, you think about it, smart cities. So these applications are basically giving you money that solve this problem. I want a smart city. Now, what all smart city will have? It will have huge number of sensors, the water wastage, water quality, power management, traffic management. Everything should be very, 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 very controlled, monitored, and so on. Now, to do that, you need lot of sensors, you need huge compute power. So that's the need coming from. So now technology provides constraints. Transistors can't be made smaller than this. Data cannot be moved beyond, let's say, 10 millimeter distance without compromising the speed or without burning a lot of power. So these are technological constraints. So application requirements are coming, technological constraints are coming. We are sitting as a system designer, computer architects as a bridge between the need and the possibilities and providing the best solutions. So basically, one example, as I suggested, was this multi-core, moving from single core to multi-core. So the application needed more compute power, but more compute power was not possible because of heat issues or power density issues. So that was the constraint. So architects thought about it and figured out that, okay, instead of one core, make it multi-core. Now, so that's why it's very, very important, and especially the stage where we are now. So far, many of the solutions, whatever, let's say, other countries have developed, we have kind of adapted it. But if you look at it, the whole world is moving towards optimization. Otherwise, why company like Google need to make a chip? Google is famous for their software algorithms. Google has come up with their TensorFlow processor. Google phone actually uses that. Companies like Apple, which started with Intel chips, now they have their own chips for their laptops. Because if you don't have the control of at least a large part of these abstraction layers, you will not be able to optimize any further, because all the low-hanging fruits have been taken. So if you really want to improve compute power going forward, we have to have the understanding, we have to learn where the bottlenecks are, and then work towards basically addressing those bottlenecks. There are other trends also. So I'm just highlighting the trends. So now when we move to multi-core, the initial thoughts were that, okay, earlier I had one x86 core. Now I will have 4 x86 cores, and that's how I'll get more and more performance. So basically, all the multi-cores will be homogeneous. And when many of the Tylera processors are actually based on this assumption, and they are built on hundreds of homogeneous cores. Now, it has all its advantages also. You don't have to think too much about how to map application to the processor or to the hardware, because all the hardware are same, so you can map any application to any hardware. Communication becomes seamless because everybody talks almost in the same language, so you don't need any protocol conversion, etc. But this was not very optimized, because if I need to put, let's say, 10 x86 cores, and I have an operation which is more like a DSP operation, so I rather put a DSP core instead of a general purpose CPU. And that's the trend which we see in real life happening. So if you look at the energy efficiency, basically memory operations per second per milliwatt, you will see that the general purpose processors have a very poor performance. General purpose DSPs have better performance, but if you think of a dedicated hardware which is only designed to do that particular task, let's say an MPEG encoder, then the energy efficiency is much better. And this trend is basically very much evident in industry as well. So this is the diamonogram of Apple A12 system on chip. Now, if you look at closely in this diamonogram, this part which is highlighted has specialized accelerators. So you see almost 50% of the chip is full of specialized accelerators. So, and this trend is going to continue. If you look at the trend from their early days processors to today, we have more than 40 very specialized accelerators in each of these chips SoCs, and going forward this number will go this number will increase further. Now think about it. So we agreed that to solve the performance problem we need multi-core. Initial thought was homogeneous multi-core. That's not giving us the required performance. Now we are moving towards more specialized accelerators or a very heterogeneous system. Now, when you have this kind of heterogeneous system, the design becomes very challenging, and you have to be very, very confident, aware of what is going on in your design. So if we basically show it through this kind of cartoon image here, we can think of currently we are on the left side, where by a powerful SoC, we mean that there will be some GPUs, inbuilt CPUs, and few accelerators in it. Now, in this SoC, there are some shared resources. What are those shared resources? The caches, the memory is one important shared resource, and the interconnection network. Because interconnection network is something which will be used to move data around. And if this trend continues going forward, we will have much bigger SoCs with many more GPUs and much more accelerators and CPUs. They will still have that shared network on chip and the memory. So I'll come to network on chip little later, maybe in few slides. Now, among various challenges, let's say I am an SoC designer today. I have to come up with a particular solution, particular SoC, and I have a very little time to market, because you see that your smartphone processors are evolving every 6 months. There is a new version of smartphone processor. Now, when you are at working at that speed, of course, you will be relying on platform-based design. So you will have some platform, and you will be sourcing different kind of IPs from different vendors. For example, someone has a very efficient IP for let's say image processing, or let's say simple video decoding, etc. So you will use it in your design. You are not going to design it from scratch, because that will be way too complicated, and you will not be able to meet your timelines. Now, when you bring that IP from third party, he mentions some specs. He says that, okay, this IP will require this much of private memory, this much of dedicated, let's say, shared memory to give this kind of performance. So it will come with some performance specs. Now, if you just in a very naive approach, you take this and with the specs mentioned, you try to design your SoC, and of course you have to spend most of your 90% of your time in validation, whether when you put these things together, they work as expected or not. Now, before even you go to validation, you will see that it's very likely your memory budget, your power budget will blow up very quickly, because all these IPs which you have sourced from third parties, they are their specs are mentioned for, let's say, a typical performance, and if you keep that kind of memory, that kind of power budget for each of these IPs, you are assuming that all your IPs will be working together, which is not the case, right? So you will be over budgeting your design. So you have to be intelligent and figure out like how much actually you need to budget for each of the IPs, etc., so that you can optimize there. Otherwise, these things becomes very difficult to implement in a budget. So we have some work. I'll not discuss it today regarding this. Basically, design space optimization for this kind of heterogeneous systems, where possibly you can share memory, you can share interconnect in a better way. Feel free to look up some of the things which we have done in this space. Now, coming back to the interconnect. So here we briefly mentioned about network on chip, but what is network on chip? So let's get there. So as I mentioned, like from von Neumann onward, every processor, every computer we have designed, it works on this processor and memory, and then there is a bus in between them, so that whatever data I need, I can get it from memory, whether it's instruction, whether it's data, and the processor works on it and sends the data back. Now with multi-core, the scenario looks like this. We have the bus and we have many processing elements connected to it. Now bus being a shared medium, so by shared medium what we mean? We mean that only one pair can communicate at a time. So let's say this processor wants to communicate to this processor, so it will request for the bus access. So once it gets the bus access, it will be able to transmit the data to this node, but no other element connected to the bus at that time will be able to use the bus. Now you see that for small number of elements connected to the bus, this is still okay. But when you are talking about connecting 16, 32, 64 different processing elements and they are sharing the same bus, it becomes very difficult, because bus becomes the bottleneck, right? You have to wait for the bus a huge amount of time before you get access. So even if you have processors, they will be sitting idle because they will not have data to work on. So so in the early 2005 or so, this problem was becoming very prominent. So remember that around 2000 multi-core came, and by 2005 or so, it was very obvious that the concept of multi-core will not work if all the multiple processing elements are connected to bus. So what is the way out? So, and we are talking about thousands of core. Actually, there are instances where people have built processor with thousands of cores. Bus is not scalable. That is the bottleneck. So the way forward is called network on chip. Now, what is network on chip? So network on chip says that instead of this single bus interconnecting every node, you create a network. So what is this network of? This network is of dedicated routers and basically interconnects. So routers are connected through this segment of interconnects, and each of the processing elements is connected to a router. So whatever the processing element wants to communicate, it sends the message. Basically, it's a, as you can imagine, it's a scalable solution, because now if I from 16, if I need to move to 64, I have to just extend this network, and the communication and computation are decoupled. So how? So computation is done by processing elements, and whenever something needs to be communicated, it is sent to the router. Now router looks at the source destination and figures out how it should be routed. So the processing element is no longer involved in routing the messages. Okay, so if we want to pictorially see it, let's say this is a packet, and this packet needs to move to, let's say, P16. Now the packet will move in multiple hops from its source to destination and reach there. Now, of course, it's a multi-hop communication, and uh, still it's better because it's not as bad as the bus-based system. It also consumes significant amount of power. So these routers are not cheap. They in a typical chip, if you look at even the recent studies, it shows that 60% of the processor power is consumed for data movement only. So it's a huge amount. So if you can save something there, that will be significant. Now, one thing is very obvious, that the communication becomes multi-hop, and as your system becomes bigger, long distance communication will take longer time. So can something be done in this regard? So there are again lot of work in this domain. So typically this interconnection network which I'm showing here, it's called mesh because it's a regular mesh kind of a structure. Now one idea is, okay, you have mesh. Can you put a few long range links on top of this mesh, and you can decrease basically if you put few long range links in this mesh, the average hop count which this network has will drastically go down. And this is a very standard network theory called small world network. So small world basically is basically there are few nodes which with lot of connections and so on. So basically to achieve that, many researchers have come up with many interesting ideas. Different kind of emerging interconnects are used, because you can think of how can I just connect this router with this router, let's say through some copper wire. Now you can do that, but that copper wire will be, let's say around if you route it properly, the length of that copper wire will be in the range of 10 to 15 millimeter. Now 10 to 15 millimeter long copper wire will be pretty slow, right? So even if you have a long range link, you will not be able to communicate data very quickly. So to address that, or to have very basically feasible long range links, people have come up with optical interconnect. So basically you augment your CMOS chip with few optical long range links. During my PhD, we proposed to have on chip millimeter wave wireless. So millimeter wave, which is 60 basically 30 to 300 gigahertz, where the antenna size is manageable, so you can actually fit in wireless transceiver inside the chip to communicate long distances. Now the wireless also provides advantages, because I'll come to the specific advantage of wireless little later, but let's see how the communication now will happen. So let's say this node has a wireless. So basically you can go to the nearest. So basically you can go to the nearest node with wireless, and then go to the wireless receiver, and from there you can move to the destination. So your average hop count has drastically gone down. So again, there are a lot of work in this regard, and there are very interesting ideas also related to that. Yes.
If I use the wireless millimeter wave sensors or something, the antennas, if they are in the close proximity, they cannot create a noise or something interference.
So they are not that close. So basically, they are at least, let's say, 10 millimeter apart, and there are studies which basically had design rules that how to avoid this interference. For example, you can create a vacuum kind of thing just below the antenna, so that the transmission doesn't happen through the substrate. Instead, it goes through air. You can put basically enough Faraday cage kind of thing, so that the transmission doesn't go out and so on. So, and this has again picked up a lot of momentum, primarily now because of the chiplet interconnections, which brings in very new dimension. And if we think about it, we have very stable Bluetooth connectivity between all of our NFC is very stable, right? So it's just squeezing it a bit and saying that, okay, can I do it in a, let's say, 40 millimeter by 40 millimeter area? Okay, so in this regard, we have a very interesting work which was published in Transaction on Computers in 2017, and we call it hybrid wireless interface network for heterogeneous systems. So I'm not going into the details of the paper, but the very broad sense of the paper, it says that especially when you have heterogeneity in your system, as I have shown that there will be a cluster of GPUs, cluster of accelerators, cluster of maybe CPUs, and so on. Each of them require different kind of topology, different kind of optimization to interconnect. So this paper says that what we'll do, we will take these clusters and optimize them, or basically get them in an optimized form, and then sandbox them from each other. So they are completely isolated from each other. And whenever they need to talk to each other, they will go via wireless. The advantage is, if you do it any other way, you have to have some kind of protocol conversion. For example, let's say GPU is a very, very throughput sensitive cluster where you need data, huge amount of data, whereas CPU is a very latency sensitive cluster. Put them together and they are connected through the same interconnect, and there are experiments which shows that, for example, let's say I want to run some experiment. I have a CPU only machine and I have a GPU only machine, so independently they work better. If I have a machine with CPU and GPU, both of them basically suffer in terms of performance, because the shared medium, primarily the interconnects, are hogged by GPU and CPU gets stalled. And similarly, GPU, when it is waiting for a huge amount of data, maybe CPU has taken up some share of it. So that's why putting them together is not a good idea. But if we can sandbox them, and then in a controlled manner we allow communication to happen between them, that gives much better result. And for this communication, now if I use some kind of a wire to make this communication, for example, let's say GPU is working at 2 gigahertz and CPU is working at 1 gigahertz. Now if I want to communicate, so I have to have some kind of a protocol conversion in between, so that voltage, possibly the voltage levels they are working on are also not same. So all these conversions will have to take place in between. So but with this hybrid wireless NOC strategy, you can avoid all of them, because it's kind of a common language which they can use to communicate. So basically GPU also uploads data which need to be transmitted wirelessly, and CPU also receives that as a wireless reception, and then keeps basically works. Sorry, the graphic is not coming. Oh. So there was basically there were 4 heterogeneous subnets drawn here, and the communication bit. Sorry about that. So basically, inter subnet communication happened through wireless. Intra was happening through inter was happening through wired. Inter was happening through wireless, and so on. So okay, that picture is not visible. Okay, so I'll stop here a bit, and if you have any quick question, I'll be able to. Yes.
I want to know that as you are mentioning about antenna
Mm-hmm.
or that NOC.
Yes.
So is it possible to hack that communication from outside?
Uh,
Because you are having an antenna.
Yes.
It is basically
Mm-hmm. Absolutely, absolutely. Yeah, security is a huge concern.
If you are having a 60 gigahertz, it is not possible. But if you are maintaining any millimeter wave, maybe 30 or 40 gigahertz, is it possible to communicate?
It's basically it can be prevented, but of course you have to make sure that you make it secure. So that even if somebody, let's say, they can jam also, right? So
Yes, that's right.
so we have to take precautions so that those things can be prevented, of course. And now with 5G around, so even it might.
6G is coming.
Yes. So
And
this.
my second question is that we are basically thinking about silicon as a base. So maybe copper is very lossy because that's why you cannot have that part. But nowadays, graphene materials are coming in features. So how you can incorporate this graphene in this NOC?
Yes. So we also did study about this. Graphene is an interesting thing. People are working and still working on graphene. So even CNT based antennas looked very promising because the size only and it could also sustain very high frequency compared to what, let's say, millimeter wave. So bandwidth will be huge, almost like optical. The challenge is manufacturing reliability. Yeah. So once that gets resolved, of course, this could be a very good solution.
I have a question.
Yeah.
Maybe the question is a little bit different.
Yeah, sure.
You are placing the processors or the components in different using different type of topology, maybe mesh topology, or maybe you're trying to reduce the connections using the wireless. So still, like we need to connect between different processors, the components. So do people use any meta heuristic kind of algorithm there to like kind of the optimal setups of the components?
Yeah.
It's
So
difficult to find out the actual
true.
best solution for this because the components would be
Yes.
quite large.
Yes. But yeah, it's a very important point, because let's say not possibly all for the specific application, not all of them will be talking with each other, right? So can I profile my application and figure out which are the nodes which will be more frequently talking, and then make my interconnection network tuned to that. So all these things basically, which it kind of indicates that can we do something, some framework which will dynamically allow me to allocate bandwidth depending on the need. So there are works also going on in that direction, and for that you need this kind of flexible let's say interconnections, which, for example, in case of wireless, if I have, let's say, a lot of data communicating between this node and this node, so I can permanently keep them connected, and I don't allow, let's say, the other two wireless transceivers communicate. So these kind of dynamic things you can do.
So maybe this may be some kind of like application specific.
Yes.
Like for some applications, some components maybe they will interact. So
Yes.
they,
Yes.
interconnect.
Yes. Yeah. So also the other interesting part is depending on your data rate need, or basically the need of bandwidth, you can pump in more power so that your BER or signal to noise ratio and BER can be played with, and uh, even the distance you need to communicate. So not necessarily all these transceivers need to transmit at the same power level. And this becomes even more important when you talk about chiplet, because inside a chip still the area is limited, but when you are talking about chiplets, there are multiple dies, so that distance is reasonably longer, and you can use dynamic basically power amplifier, which will, depending on the destination, will pump in more power or less power. Yes.
So, the one that you were just talking about, my first question is how are you going to decide that where you're going to put the wireless points?
Yes.
Okay, because that need to be optimized.
Yes. Yeah.
Okay. Another question is like when you said that the copper is very lossy. Another one the topic that we got is just like you can use graphene. Graphene is just like you have a manufacturing problem because there is a very challenging. So why can't you use in between that any other metal? Like,
there are.
I can be wrong.
Yeah. No. You are absolutely correct.
Okay. silver or gold or something like that? Can't you use that?
Yes. To great extent, it can be used, but the kind of bandwidth you are looking for, so it's boils down to RC delay, right? So either you make your wire very wide, and especially those long wires, uh, basically routing them is also a difficulty, because your top metal layer, which are the widest, they are reserved for VDD, ground communication, clock communication. Now you have another wide. So basically what we are looking at is uh, efficient wires. It can come from anything. So there are so basically, though I have highlighted about wireless, optical, graphene, etc., there are other solutions which are based on copper as well. People have come up with, let's say, optimally buffered wires which can sustain certain kind of bandwidth and so on. So those are also there. But the kind of benefit you get when you move to optical or, let's say, wireless, uh, wires might not be providing that. So there are pros and cons. So it's all about trade-off, how much you can spend and what you want to get. Yes.
Another question is like, why you're communicating with wireless?
Mm-hmm.
You have to do a frequency modulation or something like that. In order so that interference is not there.
Yeah.
So you need to decide in what bandwidth and what frequencies.
So yeah, so the band, the millimeter wave band is basically 30 to 300. So we, at least in our experiments, we used 60 gigahertz, 120 gigahertz in that range. In terms of modulation, we went to, because we don't want to make things very complicated, right? So that's why we went ahead with simple modulation like OK. Of course, it doesn't give you very good bandwidth, but the implementation becomes much more easier. On-off keying.
The bandwidth also increases with the number of processing elements, because the number of wireless elements will also increase, right?
No, the bandwidth provided by wireless will be depending on what kind of modulation scheme you use. For example, if you use OFDM, you will be able to achieve much higher bandwidth compared to if you use OK, on-off keying kind of thing. So basically you can only send 1 or 0 at a time.
Oh, so why can't you make a hybrid system like use of buses along with this wireless system?
Of course, it's not either or. I'm just highlighting that. So here, if you think about it, if you visualize it, the wireless is kind of acting like a bus. It's a shared medium, right? So if I want to use wireless, it's more like a bus. I request for wireless, I get it, and then nobody else can use it. And then I release it. And the local communication is happening through wire, which is happening through the switches and the interconnects.
That's what I was asking. Like you're using one single frequency, like for communicating. This is the reason that you cannot use it for like multiple
concurrent channels can't happen.
Okay. So why if you use if you use different frequencies for different,
the transceiver becomes very complex. You can do that, but the overhead you will have, for example, OFDM you can use. You can have a OFDM transceiver. Yeah.
You have to use new model.
Yes.
That's why I'm thinking that suppose I want to send a data to P1 to P16, and then at the same time, let's say P5 wants to send data at the same P16. Then if they both wants to use that W1 wireless channel, then there must be a priority.
Some arbiter.
Some has to go faster, some has to go low.
Yes.
And then there has to be a latency problem.
Yes. So proper arbitration has to be there to make sure that these things. Okay. So very quickly, I would move ahead. So another thing, when you are talking about this complex system, as you can imagine, there is a possibility of your system getting basically having bugs at different stages of your design. And as I mentioned, like as a system designer, you will be primarily sourcing your different IPs, putting them together and validating. So validation becomes very, very important. But these things are so complex, then whichever way you validate, you still might miss something, which will be manifested when you have the silicon. And that's why it's a very common practice to have basically debugging at the first silicon which comes out, right? Before you go for manufacturing, you basically have some inbuilt debug structures. So like trace buffers, which will be collecting traces, because once you have the silicon, you have very little observability, controllability inside the chip. So that's why you will put different buffers in between, so that you can extract out what was the, for this stimulus, what was the status of these particular buffers. And these are called design for debug. So basically, while you are designing, you will have that design for debug strategy, and those design for debug resources you need to put inside your chip. So okay, I'll quickly go ahead and we'll talk about how using this kind of proper interconnection strategy, we can even make this design for debug strategy better. So what we are talking about, so this is our circuit under debug. Then there is this design for debug structures. So they have this trace buffer unit, there is a trigger unit. So if the trace buffer is full, the trigger will go on, and then the traces will be sent out to the off-chip debugger. So typically, and then off-chip debugger will determine whether your chip is functioning fine or not. So basically, let's say this is a packet which moves inside your SoC, and it generates a trace. So you collect those traces and keep on collecting those traces till your trace buffer is full. Once it is full, you bring it out, you observe whether everything is working fine or not. Now, in one of our work, what we have done, we have tried to expedite this process using the proposed interconnection network which we have, and basically use this to our advantage so that the debugging can be done quickly. So what we have done, and there are studies which shows that with wireless, how your basically average hop count goes down. So basically, if your average hop count goes down, your amount of traces also goes down, right? So your trace buffers are not filled as quickly as it was earlier. So here in the debug stage, what we do, we collect all the traces, and then these traces are collected to these wireless hubs. And from these wireless hubs, we can basically transmit these traces back to the off-chip debugger, which is much faster than your JTAG, because JTAG is a serial communication. So amount of trace data transfer will take much longer compared to this wireless transfer. And this work was published in basically TCAD, IEEE TCAD in 2020. And yeah, in the interest of time, I'll quickly move ahead. Now, once we have this debug structure, so then we started thinking that, okay, this debug structure, once it goes to the mass market, those debug structures are unused. For example, whatever this design for debug, trace buffers, and other elements you have put in your design, they remain unused once you are out of this debug phase. So can we reuse them for improving our interconnection network? Because ultimately, if our interconnection network improves, data movement will be better, and we can run our algorithms better. So what we propose that, okay, we have these trace buffers, which are nothing but memory. Can we distribute these trace buffers in our router as virtual channels? So each router, so I have not gone into the details of this router. So these routers have different ports, and each of these ports have input buffer. And for better management of input buffer, instead of putting only regular buffer, we call it virtual channels. So basically, it's like multiple parallel paths to enter a highway, so that if one path is blocked, your message can go to the other path. Now, can these trace buffers can be redistributed into this as this virtual channels in our switches? So we have done that, and we see that basically we can get significant amount of throughput improvement. There is a hardware called trace prioritization hardware for which is used in the debug stage. So we used or reused this trace prioritization hardware for critical data prioritization. So instead, in the network, instead of sending all data with the same priority, we use this trace prioritization hardware for identifying which is the most critical data. So basically, mixed critical data can be handled better way. Using this trace prioritization hardware. Also, there are packet monitoring modules which can be used for starvation control, so that basically no node is waiting for its chance longer than a stipulated time. And this paper was published in TETC very recently. Then as somebody has already pointed out, that this wireless being a shared medium, we have to be very efficiently using this wireless medium, so that the critical data gets its share of wireless channel at the appropriate time. And our observation and intuition also says that the traffic density and the data criticality will not be same all the time. So typically, to keep the access mechanism very simple among the wirelesses, it's generally done through round robin fashion. So basically, let's say you have 4 wireless interfaces. First one gets its chance, then the second one gets, third and fourth. Now, this will be not very optimal, because it is not aware of the data criticality or whether the data availability as well. So now, one very crude way could be, we have a centralized monitor which observes that, okay, where critical data is or where data density is more, and then it tells that wireless interface to get the channel and communicate. But to gather this information, you need a lot more. Basically, it will be much more complex. So what we have done, we have come up with a very distributed system. So where each wireless interface will learn gradually from each other, and they will keep a ranking table with themselves, and periodically that will get updated. That ranking table will depend on the amount of data they have, as well as amount of critical data they have. And basically, with this approach, we could very efficiently use the wireless medium for data communication. And this paper was published in Journal of Emerging Technologies in Computing Systems. So I'm rushing through. I'm just trying to introduce you, and I'm giving you the links. So please feel free to go, and if you are interested, get in touch, or you can ask if you have specific questions also. Some of the details are mentioned in the slide. Of course, there are a lot of things which are in the background. So I'm just trying to give you a glimpse of what can be done and what we have done so far. Another very interesting thing in case of multi-core is this coherence. So as I was mentioning about, the coherence protocols were designed assuming that all your processing elements and peripherals are talking through a bus. And that's why, by this assumption, basically broadcasting, all the protocol designers assume that the broadcasting is by default. You can very easily broadcast messages among your peripherals, etc. But this was true when the systems were designed using a bus. But when we moved from bus to network on chip, this became a huge nightmare. Why? Because network on chip is not an ordered network. So what do I mean by that? Basically, if I am a receiver and I receive two messages, I don't know which message was originated at what time, because this is a completely distributed network. Some source generates some message, it comes to me after 4 hops, and some other message was generated, let's say uh, sometime later, and it only came through 2 hops and reached me at the same time. But I don't know that the earlier message was generated first and this message was generated later. Now, why it is important? It is important because the coherence protocols, especially Snoopy, what it does, it says that, okay, I'm going to use this block of data. So if you have a copy, invalidate it. So it generates an invalidate message. Now it's very important for me to know the order of this message generation, because if I receive this invalidate this block of data, then I will assume that, okay, whichever message receives to me, that node has generated that message, but that might not be true, right? So that's why implementing Snoopy in a network on chip is difficult, because you don't know who has generated that invalidate message. Because let's say P3 and P4 both want to use the same block of data. Both of them generated that, let's say P3 generated that message, invalidate this block of data earlier, and later on P3 also generated that message. But I, as a P7, maybe I have received the message from the P which generated the invalidate message later first, and I'll assume that, okay, now the ownership lies with the P3, but that is not true, right? So that is a huge problem. So to address this problem, what we have done, we have proposed a solution where basically the heterogeneous subnets among themselves keeps coherence or maintains coherence through directory protocol. Directory is another protocol where basically you maintain a directory about all the sharer information. Now the problem with this is basically, it's again, scaling is an issue, because you, as number of sharers becomes larger, you have to maintain a bigger table, so you need more memory and so on. So if you want to maintain coherence among small set of nodes, then directory is fine. So that's what we have done. We have implemented in the subnet directory based protocol, and among the subnets we have maintained Snoopy. So this is one of the very unique approaches which we proposed, basically Snoopy over directory. In coherence related papers, you will find a lot of papers where people talk about directory over Snoopy. But this is the first approach where we said that we can do it in the other way, and we could do it because we were using wireless to implement the Snoopy. Because with wireless you can broadcast messages very easily, because all of them are working at the same frequency. So you can just basically, just like exploiting the bus kind of nature of wireless. And this was published in Todes. And yeah, going ahead, almost the similar kind of strategy we extended for chiplets. And and we maintained coherence among chiplets using this wireless interfaces, and this was published in VLSI Design recently. All right. So I will stop here, and I'll briefly introduce about my lab before I conclude. But if I'll be very happy, I'll be very happy if you have any questions. Uh, yeah.
So as we know that in case of wireless sensor networks,
Mhm.
they have civil attacks, wormhole, and so many attacks.
So in a complex structure, when there are a lot of data are going and coming, so in that structure, if cycle or wormhole or black hole attacks to that, then how it could be possible to overcome?
Yeah, so you see that it's not as open as wireless sensor network. There are very basically you are talking about communicating wirelessly in a very constrained environment. You are not making it open. So a very easy way to control it could be, I can say that I'll put everything under Faraday cage, so nothing can go out, nothing can come in. So basically you will not be able to attack. There will not be any electromagnetic exchange outside this Faraday cage. So that way I can prevent it. But in general, security is a big issue, and we have yes. So you have to be very, very careful. So we have again some work on security domain as well. So basically, if you can identify, let's say some node is creating unnecessary packets and try to create a denial of service kind of attack, can I identify it? Can I also distinguish that okay, this is a genuine node which is generating useful packets, compared to a malicious node which is generating some kind of let's say denial of service attack. So for that also there are techniques. So you can create a group of nodes which collectively will basically through some voting etc will decide that whether this node is the one which is generating useless packets. If so, then can we basically that node will be isolated and you will reconfigure your network so that that isolated node is not no longer affecting your communications.
The second question that you talk about the snooping. Is it related to the MNP protocol?
Can you repeat?
MNP protocol.
What is the full form?
The full form I don't know. That's related to the protocol, the structure that is the wireless and the MAC protocol.
It's not exact. No, it's not. So basically, in computer networks, so when you are talking about shared data, so generally your memory is structured like this: that your processing element has some private data, and then some shared data. Now, shared data, as the name suggests, it can be shared by other processors also. Now, how do you know that the copy you have is updated one or not? So it says that whenever somebody wants to work on some blog and it wants to move it from shared to private, then you should let others know that I'm updating this data, so that if you have a copy, invalidate it and get a fresh copy from me. That is broadly what is maintained by this coherence in computer.
Routing table.
It's not routing table. It's about sharing table. You can say sharing information. Okay, so before I conclude, I would like to briefly introduce about the Advanced Multicore System Lab. So we are doing or working on different things in our lab, starting from interconnection network on chip, accelerator-rich system design, design for debug, hardware security, and also on low-cost health monitoring systems. So I think some pictures are missing. So actually, I had a group photo. So all these works are primarily by the PhD students. So most of the papers which I have shown are either from Siddharth, Mitali, Harsha, who are the alumni of this group. And then we have a big group now working on this thing. So I'll also briefly introduce the alumni of the group. So Hemanta is right now at NIT Durgapur. He was my first PhD student. Harsha, he is now in ARM, leading the NOC IP group. Mitali, she initially joined IMEC, now in basically Shell. And Siddharth, he is in ST Microelectronics. Yeah, so these are few collaborators I work with, and in a nutshell, if you look at the kind of work we are doing, it can be classified on basically interconnection network, validation, security, and performance and power. And I have also highlighted some of the important work in this domain and the publication. So thank you for your attention, and I'll be happy and available over these links to answer further questions if you have any. Thank you.
Thank you. Thank you, sir. Great talk. I must say, because nowadays, I'm just emphasizing everywhere that government of India is thinking of a boost in semiconductor industry in India. Many people are working in this domain, even not in the main domain. They want to build startup in India. That's why new program Chip to Startups actually started. And people are not emphasizing currently in many universities, many institutions on this semiconductor domain, especially in VLSI. There is a big problem in our mindset that VLSI and device, they are same. That's not same. You can do many research in lower frequency domain in VLSI and in higher frequency domain in VLSI. And we are also thinking of doing this millimeter wave VLSI thing. And RF VLSI is a big challenge nowadays. So means I'm thankful to Professor Dev about emphasizing and really a new interesting topic. So
Thank you.
sir. Thank you.
Thank you, Dr. Sujoy Dev, for your special talk on efficient compute platforms for enabling the artificial intelligence revolution. Now, I would like to invite Dr. Abhinav Dhol to present a memento to Dr. Sujoy Dev. Sir, please. Now, Dr. Abhinav Dhol, I would like again to invite you to present a memento to to Professor Syan Chatterjee. Thank you, sir. Now we will have tea outside the seminar hall, and the next session will start at 4:30 p.m. So please be seated till 4:30 p.m. Thank you.